dia, pessoal. Tudo bem? Bom, vamos começar o segundo dia de Good Morning Simulation, correto? Para facilitar a minha vida aqui, eu trouxe o cara que apresentou ontem, né? O Leandro está aqui do meu lado. Leandro, queria que você fizesse um resumo um pouquinho do que foi falado no primeiro dia. Primeiro a gente teve uma edição especial do 3DXcast, né? Uma edição extraordinária do 3DXcast. E a tua apresentação, conta um pouquinho, faz um resumo do que foi falado ontem, no primeiro dia.
Legal, legal. Bom, no podcast nós só tivemos aí uma troca de informações, nós trocamos um pouco de ideia, principalmente com o pessoal que atua no mundo todo, né? Realmente o Hassan, que ele trabalha mais nessa área de eletromagnetismo, e o Ramesh, que ele trabalha mais nessa parte de cálculo estrutural, escoamento de fluido, eles atendem diversas empresas pelo mundo todo, então foi só um bate-papo entre eles, pegar um pouco da experiência deles, foi muito legal, foi bem importante, exatamente para poder passar aqui para o pessoal, para as empresas aqui no Brasil, como a gente pode adaptar, como a gente pode utilizar essas tecnologias que já existem, já estão aí, já a tecnologia, exatamente para desenvolver componentes cada vez mais leves, eficientes, inovadores. E na minha apresentação, André, eu abordei a questão de simulação do processo de injeção plástica. Ou seja, durante o processo de injeção plástica, né, ele é um processo complexo, que é uma mistura de tempo, temperatura, como a gente pode fazer a calibração da máquina. Às vezes, algumas empresas compram um molde que vem da China, que vem da Índia, que vem de fora, e a gente tem uma brincadeira nessa área, André, que às vezes precisa pintar o molde de verde e tacar no mato. Por quê? Porque não injeta peça, não injeta peça. Então mostrei também alguns exemplos reais de aplicação, como pega esse efeito de warping, né, de distorce da peça, se a peça vai injetar, se não vai injetar, ou seja, uma visão geral de como a tecnologia do SolidWorks Plastics auxilia as empresas nesse desafio.
Legal. Bom, esse foi o primeiro dia.
Isso.
Né? Quem quiser assistir o primeiro dia, dá para assistir, é sob demanda, né? A gente faz o lançamento ao vivo, mas depois ele fica disponível para você assistir também. Mas, Leandro, vamos dar um spoiler, então, do que vai ser apresentado agora. Qual que é a próxima apresentação que a gente vai ter hoje no segundo dia?
Joia. Nesse segundo dia, pessoal, nós teremos a apresentação do Hassan. O Hassan, ele é um libanês, que ele vive na França já há mais de 20 anos. Ele é doutor em eletromagnetismo, ele tem um grande conhecimento técnico e também atua em todo o mundo. Ou seja, nós vamos ilustrar a tecnologia Simula CST, que foi uma tecnologia que a Dassault adquiriu faz mais ou menos uns 6, 7 anos, e faz com que exista a possibilidade de simular efeitos eletromagnéticos tanto de baixa quanto de alta frequência. Ou seja, tanto essa parte de dimensionamento de motores, motores elétricos, rotores, como também essa parte de antenas, que envolve a parte de eletromagnetismo de alta frequência. Espero que vocês gostem do conteúdo, pessoal, e novamente nós estamos aqui no Brasil, totalmente disponíveis para suportá-los em todos os desafios para todas as empresas aqui da América Latina.
Boa. É como ele falou, a gente está aqui, localizado no Brasil, mas a gente tem escritório em vários outros países, né? No Chile, na Colômbia, na Argentina, temos representação em toda a América Latina, e esse time, esse exército que a gente tem, está preparado para te atender em todas essas conversas, todos esses assuntos que a gente vai apresentar para vocês, eles estão totalmente preparados para atender vocês. E óbvio, quando precisa a gente bota esse cara no avião também.
Joia.
Garbim,
Estamos disponíveis.
Obrigado. Vamos pro segundo dia? Valeu.
Um abraço.
Hi everyone, my name is Hassan and I'm a business consultant in Dassault Systèmes, and today I'm going to speak to you about electromagnetics and what are the solutions that we can provide you to accelerate the innovation and to get your optimized product faster. So our presentation today, it's going to be divided in some parts. I'm going to give you a little bit of introduction about electromagnetics. So what is electromagnetics? Actually, electromagnetics is around us every day. Probably you feel it, sometimes you do not feel it. For example, when you turn on the light, it's electromagnetics. When you use your mobile phone, it's electromagnetics. Even when you play on your console, it's electromagnetics. But of course, we have more designs that eventually, like antennas or cars or connected systems, electronic systems, all of those products, they use electromagnetics. And it is super important to understand how your product works before putting it into the market. And our tool is going to help you to optimize your product and accelerate the time to market. And we will see how we can do this. Okay, so electromagnetics, as I told you, they exist on a broad spectrum. We call this from DC up to light waves. For example, in DC, we can deal with sensors, and in light waves, light is considered as an electromagnetic waves. So the light that is produced by the sun, it is an electromagnetic waves, in addition to the fact that it's also a particles or, quota of quantas of photons. But between these two between these two borders, we have lots of application. For example, in the hertz frequency range, we have the motors or electric motors or electric generators. Then in the domain of the kilohertz, we have the electric motors for cars. And of course, in the RF and the sub-millimeter wave, on the millimeter waves, we have antennas that actually ensure the connectivity and allows us, we shorten the distance with the connectivity that the antennas provide us. Now, I'm going to speak to you a little bit about the solvers that we have in CST. Now, CST is composed of one graphical interface that contains more than 25 numerical methods, and each numerical method is dedicated to an application. For example, we can cover high-frequency applications such as antennas, and for each type of antennas, depending on the geometry or depending on the behavior of the antenna, we have a dedicated numerical method, but also we have the exact same package of method dedicated for low frequency, for example, for electrical motors, for sensors, for insulators, you name it. Of course, we can tackle as well other type of application, as I told you, which can be eventually use several solvers, like in the electronic design analysis or the EDA market. We can use, for example, 2D solvers that allows us to simulate, for example, signal integrity, power integrity, but also we can simulate those types of PCBs in 3D in order to simulate stuff such as electromagnetic compatibility and mainly the certification. You will see just in some minutes that the certification is super important in order, and certification actually allows you to put your product into the market. There is something that you should know. Without certification, your product cannot be commercialized. And I will give you some words about this application just in a minute. Okay, so this is a more global view and all the application that we can cover. So we can see here we have the static and low frequencies where we have bushing application, magnets, electromagnets, transformers, power transfer, electrical motors, as I told you. But then we can switch gears and go to the microwave. Microwaves mean high frequency. And in that case, we can solve, for example, antennas, which are the key for connectivity, as I told you. And of course, we can simulate other high frequency devices or what we call RF devices, such as filters, amplifiers, duplexers, OMT, and all those components that are actually a part of a communication chain. Then we come to the EDA and the electronics, where basically we are dealing with the PCB board that we find it in all electronic products, especially that nowadays we have everything that is connected. So a PCB could contain traces that transmit signal, that help with transmission signals between components, but also we have antennas. So in order to ensure that the signal is being transmitted between components correctly, we run some simulations that we call signal integrity. But in the same time, the components themselves, they need to receive the good amount of power to work correctly. And here we are in the power integrity domain. Now this is 2D simulation for PCB boards. Then we can pass the information of the PCB to the 3D world in order to calculate, for example, radiated emissions. Radiated emissions, for example, are a part of the certifications that are required for PCBs, because sometimes the PCB, they produce unintentional radiations, and those unintentional radiations can interfere with surrounding systems. So this is why we have international standards that they put limitation, right, for all those radiations. And it's as simple as this. When you have radiations from your equipment that are higher than those limitations fixed by those international standards, it means that your product is not certified. Okay, and I will talk to you about several types of certification that we do, because we do not speak only about radiated emissions. We have conducted emissions, and here your product is considered as an aggressor, but sometimes your product can be also considered as a victim. And here we are speaking about radiated and conducted susceptibility. But of course, we have cable harnesses, we have shielding effectiveness, you name it, there's a lot. Electrostatic discharge is also a type of certification. Lightning strike is a type of simulation for certification, especially needed in the aerospace industry. And finally, we have the most exotic application, which deals with studying the behavior of charged particles under the effect of electromagnetic fields. Now, of course, without going a lot into the details, we can use this application to simulate plasma reactor, those devices that help us with etching or material deposition for semiconductor manufacturing. But also we can use those, for example, to create ionic thrusters for CubeSats in space, or even any type of plasma physics called plasma physics. I need to underline this this very important information. We can run this. As well, we do have a lot of most famous application for charged particle is the accelerators. One of our biggest users in the world is actually the CERN, which basically design their accelerator, or they optimize their cavities using our tools. Now, if I want to speak a little bit more about how our applications are divided, we can just have a look on this slide here, where we are presenting a non-exhaustive list of the application that we can cover per domain. For example, for low frequency, we have the sensors, right? Everything, in the smartwatch or the smartphone, the thing that is allowing you to manipulate your phone is sensors, right? And this kind of stuff can be eventually simulated and optimized inside our tools. But also we can design the magnets or the electromagnets that you can find in an MRI machine. So by this, we are even touching the life science industry. And of course, we can design electric motors, whether they are circular, for example, for cars or for home appliances. But again, we can design generators because, we either create electricity from movement or we generate movement from electricity. And of course, we should know that motors, they exist in a rotational mode, but also they can also exist in a translational mode. And a big example for this is something that's used in industrial machines, robotic, aerospace, which is the actuator. Okay. Now speaking about high frequency, of course, the antenna. And regarding antennas, it's super important to study the antenna in with its environment. We are literally producing the reality. We are creating a digital twin of the reality. So antennas need to be simulated in their environment, whether your antenna is integrated in a phone or is placed on a pylon, for example, for 5G application, or if it is on the fuselage of an aircraft, or it's used within your hand. You need to consider everything. And our tool allows simulating this kind of, context, let's say. And for your information, we do have eventually a library of biological model that you can use, for example, to study the interaction of the electromagnetic field with the human body. Because a human safety with regards to electromagnetic field, it's a domain that is super important. And this is what we call the radiation hazard. Every time, for example, in the 5G or 6G protocols, every time we need to be sure that the waves will not be harmful for the human body, right? Even if you go in to the hospital to do an MRI machine, the doctors will ask you if you have an implant inside your body. And this is not a question just out of the blue. The interaction of the electromagnetic field with your implant can harm your tissue. And this is basically, for example, the companies that who deal with fabricating implants, they must run this kind of certification to make sure that their implants are safe to be used. Now, in the electronics, as I told you, this is here a great example of a DC-DC converter where we can study, as I told you, the signal, how it's been transmitted between components, because we have to make sure that the signal will not be deformed. For example, if I send a rectangular signal from the CPU of a computer to the memory, we have to make sure that the memory is not receiving a triangular signal or a completely distorted signal, right? Here we are in the world of digital signal, so we are sending zeros and ones. And the idea is that we have to make sure that by the end, the receiver is not, it will be able, we have to make sure that the receiver is able to distinguish the 0 from the 1. And we can also, as I told you, speak about the electromagnetic compatibility. I will give you just some examples in some minutes. And finally, we have the charge particle dynamics, where you can see here some example of a vacuum tubes. This is a kind of for the musicians out there, this is a kind of a lamp amplifier, because the lamp amplifier, the connoisseur will know what I'm speaking about. Lamp amplifiers can support much more power, and by the way, this is why they are more expensive than solid state amplifier, right? Especially for guitarists. We can also deal with plasma reactor, as you can see here on the second part. So we can study literally the ionization of any gas to create the plasma. And finally, we have here an example of an accelerator device, where the idea is to make sure that our electron beam, for example here, and by the way, it could be proton beams, ion beams, whatever. The idea is to make sure and design the cavities in order that this beam continues straight without a lot of reflections, backward reflections, of course. Okay, now I'm gonna just spend some minutes to talk to you through some real applications that we have. Let's start with antennas. So if someday you meet a person and this person asks you, where can we find antenna? The answer is super simple. Well, antennas, they could be found everywhere, especially nowadays. You can have at home nowadays a washing machine that is connected. So a connected washing machine it means it has an antenna inside. And even if you are in China and the washing machine is in United States, you can still control it because of the antenna, okay? And of course, it's not only about washing machines, but about more products such as aircraft, connected objects, telephones, you name it. So here are some examples of the antennas, and as I told you, we have several numerical methods which are dedicated to several types of antennas, because antennas, they could be resonance, they could have small dimensions, they could be very wideband, they could be placed on a very big platform, and this is why we can our tool does have the numerical methods that allow tackling all kinds of antennas. And in addition to that, we have hybrid methods. For example, what would happen if you have a small antenna that for which you need to simulate the performance over a big platform, like a aircraft, for example. In that case, we can simulate the antenna with one solver, and we can couple these numerical methods to another one, which is dedicated to solve the problem on the aircraft, for example. We call this hybrid methods. And of course, this hybrid method could be completely bidirectional, okay? Let's speak a little bit about compliance. Now, the first step of compliance, as I told you, is the human body compliance. Whenever we speak about designing an antenna, or designing a mobile phone. Nowadays, mobile phone, for example, when you buy a mobile phone and you look at the back of the package, you can see some stickers with a value called SAR, which is the specific absorption rate. In a nutshell, specific absorption rate is the amount of power that 1 kilogram of your body is absorbing. Now, again, there are some medical standards worldwide that limit the maximum value of the accepted power. And again, we run those kind of simulation to see if eventually we are respecting those limits or not. Once again, if we are not respecting the limits, our device will not go into the market. It is as simple as this. Okay, there you go. This is the second type of the certification that I told you about. And again, this is only one example. And you can see this is one of our customers. Just to give you a little bit of a story about this domain. Even until now, when a company produces a product, any device that contains electronic boards like this, They need to go, sometimes they do not simulate, they just go to the market, to the lab directly to measure. And most of the time they have bad surprises. Bad surprises means they have to go back, they have to redesign, and they have to find the error, right? And they need to redesign and they need to remeasure. And quickly, they can have a kind of long design cycle that will cost them time and money. This is why, if you go here to the right side of the presentation or of the slide, you can see that our tool allows again to design the virtual prototype of this electronic board, and we can literally see what you cannot see in the real life, and you can see where the problem is coming from, and eventually you can intervene. And this kind of simulation can be applied to radiated emission, radiated susceptibility, conducted emission, conducted susceptibility, electrostatic discharge, shielding effectiveness, cable harnesses, interferences, all kinds of issues that you eventually may find in your electronic product. Okay, so this is an example here of a some of the simulation that we can do. So for example, here you can see after, before, and after the correction of the issue. You can see here that we have a lot of noise that is developed on the DC-DC converter, but the idea is that after placing a filter, you can see that the amount of the noise has been reduced. This is a certification simulation for a game control, for example, for radiated emission. Here we have the shielding effectiveness, and of course here we have the electrostatic discharge simulation certification simulation, sorry. And do not worry about those, I would say, those components, because we do have a library that is dedicated alone to all kinds of electromagnetic compatibility simulations. We do have a library that actually helps you with imitating the lab inside our tool. And of course, cherry on the cake, we do have a library of standards, so you do not have to think about the standards. For example, I don't know, let's take the CISPR 25 RE. CISPR 25, it's a standard for automotive industry, and you can choose here, okay, I want to simulate my product, which is dedicated for automotive, in radiated emissions. Automatically, CST will put the limit lines on the graph, and all you have to do is to compare those limit lines to the emissions that you have from your device, and you can see if it's certified or not. Now, I just would like to underline a very important information, that simulation until now, of course, will not eliminate the measurements, but it complements the measurements. But what is the importance of the simulation in that case? Well, simulation helps with optimizing the product before the prototyping. So it can, in one hand, accelerate the design cycle, but also it can help you to reduce the prototyping, right? Because more prototypes mean more money spent. And the final thing would be going to the lab to do the measurement with the confidence that your product is gonna pass the test. Now again, here we have some example on all, you see this is, for example, a comparison between the limits of the FCC standards compared to the emission of this game controller, and you can eventually see that this game controller is eventually certified. But then we can, for example, study some worst case scenario, and we can see if eventually we can keep on, we can guarantee the certification even if we have some error, let's say, in our design. Now, of course, when we speak about PCB, as I told you, we have, nowadays we are increasing the speed, the communication between components are getting higher and higher. And sometimes I think there are some companies who are dealing with 112 gigasymbol per second. Some of them, they want to even go higher, 256 gigasymbols per second. And there's no limit, the only limit is the sky in this industry. So this is why signal integrity is super important. And sometimes some of the components, they can be like programmed. This is why we can literally integrate this, I would say, algorithmic behavior of the component inside our tool, and we can do this via a package or a file that we call the IBIS AMI, okay? But we can also consider other types of files that are important for signal integrity, such as touchstone, the classic IBIS, And the most important thing is that we can couple the 3D simulation with circuit, because this is a 3D model of the circuit that we have here, but we should not forget that on the PCB, this is a model, a 3D model of a PCB, but we should not forget that on the PCB we have circuit component. And the best thing is that we can couple the circuit simulation to the 3D simulation in order to obtain the full system performance. This is the full workflow, by the way, for a PCB. So first of all, we can investigate the technology that we are using. This is what we call the pre-layout check. Then, after designing the board with, for example, tools like Altium, Cadence, Zuken, Mentor Graphics, we import the board. We can visually check or inspect the board before running the simulation, because sometimes, the engineer can make mistakes, right? And some of the mistakes, they can be visually detected before running simulation, and this is what the design rule checker can do. And of course, we can then, do the simulations of signal integrity, and we can validate or not. Because if we cannot validate, if the design here is not validated, we can go back a step forward, and this will cost you nothing. On the contrary, that if you fabricate the prototype, this is also the importance of the simulation. So once your design is optimized, you can go to the prototyping and the physical testing, but having the confidence and having the time and saving the money for your company. So here, as I told you, you can import ECAD and mechanical CAD data, because you can import everything together. We cannot just simulate the PCB, for example, if we are running electromagnetic compatibility, or thermal simulation. You cannot just import the PCB. You have to import also the chassis or the mechanical CAD data. And we can eventually import both in the same environment and run the simulation on all the system. And this is the kind of power integrity. Of course, we can have some results to inspect where we have the problem, where the power is dissipated the most, or where the highest impedance of the traces are. And this can help you to, know the origin of the issue and do some corrections by adding, for example, here some decoupling capacitors to reduce the impedance of this power plane. And the signal integrity, here we have an example of a communication between a CPU of a mobile phone and the USB connector, okay? And here you can see that we can have some outputs as an eye diagram, which is very important, by the way, in signal integrity. And of course, this eye diagram, you can then compare it to some specification to see if you are respecting or not the specifications. Now, a very important thing, PCB can heat. I will give you an example of a real life. Imagine you are playing a video game on your computer and suddenly you can hear the fan, turned on. This is actually because your PCB board is dissipating, or your graphical process unit is dissipating a lot of heat, a lot of power, and this power is transformed into heat. And this is why you can simulate, or you can, the fan is activated to cool down. So again, this kind of scenario, we can literally simulate it inside our tool. And you can see that we can even consider the full details of the board. We can simplify. Some engineers prefer to simplify the board. Some others would like to keep all the details of the board in order to see on each part, on each trace, on each via, what is the temperature. And of course, just before I switch to the final part, which is the low frequency, we can run, we have a CFD solver that is integrated inside CST. Within all the other tools, by the way, it's only one graphical interface. This is something that, of course, an information that is super important. And all of those simulation capabilities are within the graphical interface. So one user can run an electromagnetic simulation, whether on high frequency, low frequency, PCB, whatever, and he can calculate the dissipated power, and then using the thermal solver, whether in CFD or non-CFD, choice is his, to calculate the temperature. And to push the button even further, we can even calculate the effect of the temperature on the electromagnetic performance. So this is the final part of my presentation for today, and I'm going to speak just a little bit about low frequency applications. So low frequency, again, this is a non-exhaustive list. We have the electric motors, sensors, electromagnets, magnets, wireless charging. This charger that charges your phone without wires. This is actually a low-frequency application. We call this wireless power transfer. And of course, we have the actuators, which are the linear motors, and we have also the transformers. Now here, I think I just have an example on, some devices. For example, this is an example of an electric motor where you can calculate, everything related to the motor, the torque, the efficiency, the torque versus the speed, and we can import the full, for example, because here in the electric motor world, we use nonlinear materials. And those nonlinear materials, they have a specification called the hysteresis curve. And this hysteresis curve, we can import all of it. And of course, here we have the electromagnets, for example. We can simulate again, a transformer or choke coils, transformers. Here you can see the transformers. And as I told you, this is a coupled simulation between electromagnetic and thermal. And you can literally see the airflow above the transformer and the temperature that you obtain, because later on you can see, okay, probably my transformer is super hot and the natural convection is not enough. So you can run a simulation of a forced convection. Well, there you go. This is everything I wanted to show you today. Thank you very much. And if you have any question, do not hesitate to let us know. We will be happy to help you in any type of your, any type of product that your company is doing. Thank you very much.